Hello and welcome back to Find, Solve, Explain. Today I'm going to be doing the second question from BMO2 2023. The question reads, for an integer n greater than 1, the numbers 1, 2, 3 to n are written in order on a blackboard. The following moves are possible. The first move is, take three adjacent numbers x, y and z, whose sum is a multiple of 3, and replace them with y, z, x. Take two adjacent numbers x, y, whose difference is a multiple of 3, and replace them with y, x. So, for example, we could take 1, 2, 3, 4, and by I transform it to 2, 3, 1, 4, and by I we can translate it to 2, 3, 4, 1. Transform, sorry. Find all n such that the initial list can be transformed into n, 1, 2, all the way to n minus 1 after a finite number of moves. Will be that when you have a list that is 1, 2, 0, 1, 2, 0 and continues all the way up, when written in mod 3, you can always swap any of the values of the list. So this means that I could swap 1 and 7 in this list here. Okay, so the theoretical proof of this is, say you want to swap 3n plus k and 3n plus k, where 3n plus k is later in the list. You would perform move I twice on the number 3n plus k and the two numbers before it. Then perform move I on the number 3n plus k and the number that is now before it. Repeat until 3n plus k is in the position where 3m plus k was. Now perform move I on the number 3m plus k and the two numbers after it, and then perform move I on 3n plus k and the number after it, until 3m plus k is where it was. For example, if I wanted to swap 3 and 9 in this list, I would do I twice on these three numbers, and then I would do I on these two numbers, and then I would do I twice on these three numbers, and then I would do I on these two numbers. And now to get the 3 back to where the 9 was, I'm going to reverse the process, so do I once on these three numbers, then I on these two numbers, and then I twice on these three numbers. So now I've swapped two numbers that are the same mod when taken mod 3. Having proved this claim, we can use it to show that we can think of the list as just the numbers when taken mod 3. So the list is now 1, 2, 0, 1, 2, 0, 1, 2, 0, going on and on for n values. Now I'll make another claim. I'll claim that it works for all values of n that are 0 mod 3. And my method is to repeatedly perform I twice on on n and the two numbers before n, then do I on n and the number before it until you have the correct list. So performing I twice on these last three numbers, we swap the 9 and 7s and 8s to like this. Then we do it on 9 and 6 to give this, and then we do I on the three numbers 4, 5 and 9 to give 9, 4, 5. Then we swap 3 and 9 by I to give this, and then we do the three numbers 1, 2 and 9 again, 9, 1, 2, and this will work for all multiples of 3. And then for n, where n is 1 mod 3, so the list can be written as 1, 2, 0, 1, 2, 0, dot dot dot, 1, 2, 0, and ends in a 1, we're going to do the exact same method and it's going to work. So we swap the 8, 9s, and 10s to get 10, 8, 9. We swap the 7 and the 10. Then we swap 5, 6, and 10. Then we swap 4 and 10. Then we swap 2, 3, and 10. Then we swap 10 and 1. Okay, so we've proved that it works for n is congruent to 0 or 1 mod 3. The last thing is to figure out whether it doesn't or does or doesn't work for n is 2 mod 3. I'm going to claim that it doesn't work for 2 mod 3, and I'm going to try and prove this to you now. So when we write the list, the starting list, we have 1, 2, 0, 1, 2, 0, dot dot dot, 1, 2, 0, 1, 2. And we want this list to become something that's 2, 1, 2, 0, sorry. 2, 1, 2, 0, 1, 2, dot dot dot, 0, 1, 2, 0, 1. In order to get this first section from the list, we are forced to do some moves. At this point, it is good to notice that the move II does nothing when only considering the list modulo 3. So this list 1, 2, 0, 1, 2, 0, 1, 2, 0, continuing only with values from 0 to 2. Because it basically swaps two numbers that are the same mod 0, because the differences are a multiple of 3. Mod 3, sorry. This means that we can only use move I to try and manipulate this first list into the second list. This means we're going to be very forced with the moves we do. So starting with this first list, I'm going to use a short example. In order to get the 2 at the front, we're forced to do I here. So 2, 0, 1. And then in order to get the 1, we are forced to try and do I like this. But right now, we need a 2 here in order to get this one there. So in order to get the 2 there, we rearrange these numbers. So 2, 0, 1, 2, 0, 1. And now we can do I on these. So 2. Now we need to get a 1 here. And we can only do that if we have a 2 in this spot. So we're going to do I on this now. And now we're going to finish this and put the 1 in this spot here. As you can see, this 0, 0, 1, 2 block here is repeating, and this will always go down the chain until the very end. No matter how long this stem is, we've got a forced repeating chunk, and this chunk will repeat until the end. And here, there's not a single move we can do that doesn't reverse anything we have done already. And because none of this stuff adds up to 3, we're stuck. It's impossible to do this. So we've proved the claim, and we've shown that only values of n that are congruent to 0 or 1 mod 3 work. Thank you.